Good evening, class. This is Mrs. Komu. I just want to go over the base conversion problems that we already know about, what bases are and how to convert them. But I'm just going to briefly go over some problems. Here, the first problem says, write the base 5 numbers 1, 2, 3, 4 and 1.234 as base 10 numbers. All right. Recall that base 10 system, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0 to 9. It goes till 10 digits and then it repeats itself. It starts with 1, 0, 1, 1, and so on. This is the system that the decimal system that we are so familiar with, the base 10 system. All right. In base 5, what happens is 0, 1, 2, 3, 4. There are 5 digits. Instead of the fifth digits, this is where we'll start repeating the digits. That is, instead of 5, we are going to write it as 10. And that is how base 5 system comes. So goes. So keeping this in mind, you can apply the same rules that we apply for the base 10 system, but instead of 10, we'll just use the number 5. So without much further ado, what I'm going to do is I'm going to write this number 1, 2, 3, 4 over here. All right. Now this in the base 10 system will be what place? It will be 10 to the power of 0 or the ones place. 10 to the power of 0. Remember, anything raised to the power of 0 is equal to 1. This will be the ones place. But here it will be 5 to the power of 0. It is still ones place. Okay. And this is 5 to the power of 1. This is 5 squared. This is 5 cubed. All right. And just like the way you do it in base 10 system, you go ahead and multiply these things and add the values that you get by multiplying. All right. So 5 cube is 125. 125 times 1 is 125. 5 square is 25. 25 times 2 is 50. Plus 5 times 3 is 15. Plus, again, 5 to the power of 0 is 1. 1 times 4 is 4. When you go ahead and add all these numbers, you'll get 194. And this number is in base 10. So we have just converted 1, 2, 3, 4 to base 10. And that is equivalent to 194. Now, what about 1.234? All right, let me just write it separately so it's easy. So recall, guys, in the base 10 system, anything after the decimal point, we call it what? The 10th place, the 100th place. So if I have the decimal point over here, the place value of this one, the first digit after the decimal will be 1 over 10. The second digit will be what? 1 over 100. 1 over 10 can also be written as 10 to the power of negative 1. 1 over 100 can also be written as 10 to the power of negative 2. You guys know this, right? Again, what did I say? Instead of using 10, we are going to use 5, correct? So in the base 5 system, what I'm going to do is I'm just going to write the numbers like this, the way, and then there is a decimal point over here. There is 2, 3, 4. All right. Now this place is the ones place. That means this is the 5 to the power of 0 place. I'm going to put the decimal back. And this is in the base 10 system, we call it the 10th place. But in the base 5 system, what place is it is? 5 to the power of negative 1, 1/5 place. This is 5 to the power of negative 2, 1 over 25 place. And this is 5 to the power of negative 3. All right. Now that we have the place, the number that we want to convert and the place values, we can just go ahead and do it just like the way we did it in the first problem. All right. So this will be 1 times 5 to the power of 0 plus 2 times 5 to the power of negative 1 plus 3 times 5 to the power of negative 2 plus 4 times 5 to the power of negative 3. All right. Now, whatever calculations you do, guys, it's like simple arithmetic. So 1 over 5 to the power of 0 will actually be what? 1. Why? 5 to the power of 0 is 1. So I'll say 1 plus, this will be 2/5. You know why? X to the power of negative a is equal to 1 over x to the power of a. Remember that exponent rule? So this will be 2/5 plus 3 over 25 using the same rule plus 4 over 125 using the same rule. Now I'm going to put over 1 over here, and you guys go ahead and use make the denominators the same. Use the rules for adding fractions, and when you calculate this, I'm using my calculator, and then I got 169 over 125. All right, so 1.235 in base 5 system is equivalent to 169 over 125 in base 10 system. Yay, we finished the first problem. Now let us go to the second problem. Now, second problem, you can solve it, but it is honestly very, very logical. Let me tell you why. You have 1 in which place? You have 1 in 1/5 place. So 0.1 will be what? 1 over 5. So I'm going to write it over here. 0.1, 1 is in the 1/5 place. So it will be equal to 1 over 5. Now 0.2, it's also in the 1/5 place, but you have to multiply it with 2 because the value here is 2. So it will be 2 over 5. Just like the way we did it in the previous problem too. But you can just go ahead and take a look and you'll know the answer. Now 0.4, again, 4 is in which place? 1/5 place. So 1/5 times 4, which will be equal to 4 over 5. Got it? Now the next problem. Again, this is also, you can just look at the problem and you'll know, right? Now, there is 1 in which place? This one is there in 1 over 25th place. So this will be equal to 1 over 25. All right. And then 0.02. 2 is again in the 1 over 25th place, or 5 to the power of -2 place. Correct? So this will be 2 over 25. I'm going to go quickly here because it's the same procedure. 0.03 will be 3 over 25. And 0.04 will be 4 over 25. Again, let me repeat myself. 4 is in the 5 to the power of -2 or 1 over 25th place. Multiply that with 4, we will get 4 over 25. All right. Now here we have 0.12 in the in base 5. You have to convert it into base 10. All right. So 0.12 in base 5, you have to convert it into base 10. So I'm going to say this is 5 to the power of 0, 5 to the power of -1. I'm going to quickly write down the place value. 5 to the power of -2. 5 to the power of 0 times 0 will be 0. 5 to the power of -1 times 1, which will be what? 1 over 5, plus 5 to the power of -2 times 2, which will be 2 over 25. All right. So you have 1 over 5 plus 2 over 25. And then you go ahead and make the fractions the same. So you will get 7 over 25. You go ahead and make the denominators the same. You will get 7 over 25. All right. So 0.12 in base 10 fraction is 7 over 25. Now, I didn't leave enough place, did I? Okay. Now, D. I'm going to use the same method, 0.23. Now, 2 is in 1/5 place, and 3 is in the 1 over 25 place. So, if you go ahead and use the same procedure, you'll get 0.23 as 13 over 25. This is actually not the T problem. It's the same problem. 0.34. You will get it. You will get it as. Let's see. No, 0.43. Sorry, it's not 0.34, right? Oh, it's 0.34. Now 0.34 you will get it as 19/25. And 0.43, you will get it as 23/25. How do you do it? Same thing, right? 0.43, this is 5 to the power of 0, 5 to the power of -1, and 5 to the power of -2. Multiply these and add them all, you will get 23/25. All right. Again, it is all based upon your representation of the place value. Let us go ahead to the next problem. Find base 5 representations for these base 10 fractions. Now this is a little different. So what they did was they gave you a base 10 fraction, which is 9/25. All right. And they want you to write it in base 5. So this is in base 10. All right. Now there are several ways to do it. One way is to convert it into a decimal and go ahead and do it. But another way is change this into a representation of 5. All right. So 9 can also be written as 5 plus 4, correct? So I can write this as 5 plus 4/25, correct? Now I can write this as 5/25 plus 4/25. Why? Because when the denominators are the same, you'll add the numerators. So you have 5/25 plus 4/25, correct? Now, 5/25 can also be written as 1/5. I just reduced the fraction. Plus 4/25 can also be written as 5 squared. Got it? Now you can easily see, right? What I have over here is 1/5 to the power of 1 and 4/5 squared. Can I write this as 1 times 5 to the 1 times 5 to the power of -1 plus 4 times 5 to the power of -2. All right. That means this 1 is there in the 1/5 place and 4 is there in the 1/25 place. You guys know that 1/5 place is this place, the first place after the decimal in base 5, and then the 1/25 place is this place, the second place after the decimal in base 5, right? So I'm going to write it as point. What is there in the 1/5 place? 1. What is there in the 1/25 25th place? 4. So 9/25 in base 5 will be 0.14. All right. How about 23/125? Again, I'm going to split it up. So I'm going to write 23/125 as 20 plus 3/125, which will be equal to 20/125 plus 3/125. All right, which will be equal to, now 20/125, you can reduce it as 4/25, correct? Plus 3/125. You see where I'm going with this? So this will be equal to 4/5 squared plus 3/5 cubed. Now again, I can write this as 4 times 5 to the power of -2 plus 3 times 5 to the power of -3. All right. Now I'm going to put 0 for 5 to the power of -1 because I don't have any value over here, correct? So 5 to the power of -1 place will be 0. 5 to the power of -2 place has a value, that is 4. 5 to the power of -3 place has a value, and that is 3. All right. So converting 23/25, which is a base 10 fraction, to a base 5 decimal will give me 0.043. All right. Okay. If you were counting, problem H4A, if you were counting in base 5, what number would you say just before you said 100. All right. So 100 is, now how do you solve this problem? So 100 is in base 10. Okay. Now 100 is in base 10. I want you to convert it into base 5. All right. How do you do that? So let me show it to you very quickly. So 100, oh, where is this? Okay. 100 in base 10, right? Keep dividing by 5. 5 2's 10, 0. The remainder is 0. All right. 5 4's is 20, 0. All right. So you cannot divide any further. So go ahead and take these numbers. So 100 in base 10 will be how much in base 5? Go from bottom to the top like this. So 100 in base 10 will be 400 in base 5. Okay. Now what number comes just before 100? 99. All right. We don't even have to calculate this. So just before 100, you get 99. So 99 in base 10 will be how much in base 5? So I'm going to write 99. 5 1's 5, 5 9's 45. And then the remainder is how much? 44. Okay. 5 3's 15. 4. All right. So if I go from bottom to top, I get 344. All right. So 99 comes before 100. I took 100. I converted it into base 5. I got 344. Simple, right? Now, let me erase this. So in base 5, what is one number which is more than 344? We just saw that, which is 400. Okay. See, what is the greatest 3-digit number that can be written in base 5? What number comes just before and what number comes just after? Honestly, I have made a base 5 table. You can go ahead and do the same. The greatest 3-digit number that can be written in base 5 is 444. And just before this number, you will have 443. And just after this number, what you have is, there is no 3-digit numbers anymore because this is the greatest 3-digit number, which is 444. So then soon after 444, the greatest number you'll have is 1000. All right. 443, 444, and 1000. All right. Now, how did you do this? Now, you can write a base 5 table and go ahead and calculate it. Or what you could do is, what is the greatest 3-digit number in base 10? All right. Think about it for a minute. So what is the greatest 3-digit number in base 10? And then you can go ahead and convert it. It'll be 5 cubed, right? Because why? 5, the place value is, it is the greatest 3-digit number. So 5 to the power of 1, 5 to the power of 2, 5 cubed. 5 cubed is 125. So 125 in base 10, converted into base 5, you will get 1000. Got it? That is the greatest 4-digit number. 5 to the power of 0, 5 to the power of 1, 5 to the power of 2, 5 to the power of 3. 5 to the power of 3 is 125. Convert this into base 5, you'll get 1000. And that is how you will find out. All right. Now let's go ahead. What number in base 5 behaves the way 3 does in base 4? Now in base 4, we will count by 4s. All right. So, but you may observe that in base 4, the fourth number will be after fourth numbers, we'll go to the next, we'll make it 10, right? So in base 4, the numbers will be 0, 1, 2, 3, 4 numbers are over. So I'm going to write 10. Okay. In base 5, I'm going to count till 5, right? So 0, 1, 2, 3, 4, and then comes 10. Okay. So what is your question? What number in base 5 behaves the way 3 does in base 4? And the answer is what? 4. Okay. So base 4, 3 is the greatest digit. Adding 1 to 3 requires regrouping in base 4. Okay. In base 5, 4 is the greatest digit before you go to double digits. In base 4, 3 is the greatest digit before you go to double digits. So that is the common property. After 3, you're going to double digits in base 4. After 4, you're going to double digits in base 5. So that is the common thing. So I'm going to circle both 3 and 4. All right. Next, count by 2s to 35. Okay, 30 in base 5. Again, please remember, in base 5, 1, 0, 1, 2, 3, 4, and then you'll make it 10. All right. So if you go ahead and make a chart like that, where you'll count till 5 digits and you'll go to the next number, this is what you'll have for counting by 2s. Counting by 2s to 30 in base 5. All right. So first you'll have 2, and then you'll have 4, 11, 13, 20, 22, 24. What did I do? Every fifth number, I changed it to I changed it to 10, and then I progressed from there. All right. All right. Now in base 10, in base 5, how can you tell a number is even? So please do remember from your base 10 properties that any number that ends with an even number, or any number that is divisible by 2, is called an even number in base 10, in normal base 10 system. But in base 5 system, it is not as simple. So when you add two numbers, if it is divisible by 2, then you'll call it an even number. How do I know this? Over here, we counted by 2s, yet we have the odd numbers that we know of. All right. However, when you notice it, every odd number, if you add them, you're getting an even number. And that is how you'll determine an even number in base 5. So A is related to B. In A, you counted by 2s and you got these values. When you're counting by 2s, actually in base 10 system, when you're counting by 2s, you're counting by even numbers. But over here, you have odd numbers too. So how is that possible? So in base 5, the rule changes that when you add the digits of a number, if it is an even number, if it is divisible by 2, then you call it an even number. All right. Count by 3s until 30s. Again, you have to make a chart, and once you make a chart, you'll get it as 3, 11, 14, 22, 30. All right, these are counting by 3s in up till 30 in base 5. All right. All right. Okay, now we have the base 10 fraction, which is 1 over 2. Okay, now you have to convert 1 over 2, which is in base 10, to base 5. All right. Now there is an actually a good method to do this. So please do follow along. So 1 over 2 in base 10 can also be written as what? 0.5. All right. So I'm going to take 0.5. And what I'm going to do is I'm going to multiply 0.5 until I get a whole number. What do I multiply with? Because I'm converting into base 5, I'm going to multiply it with base 5. So I'm going to take 0.5 and multiply it with 5. Okay. And then you'll get what? 2.5. All right. And then over here, I'll write my answer box. I'll write point. I'll take the integral part of it and I'll write it in the 1/5 place, which is 2. All right. And then I'll take the decimal point or part of it again. And again, I'll multiply with 5. Again, I'll get 2.5. 2.5. Again, I'll take the integral part of it, put it over here beside my original 0.2. And then what is the remainder? 0.5. I'm going to take this 0.5 and I'm going to multiply with 5. The idea is to multiply this until you get a whole number, and that whole number will be added to the decimal over here. But this has been repeating ever since. That means this will go on as a repeating decimal. All right. So 1/2 in base 10 will be equal to 0.2222 and so on and so forth. It is a repeating decimal in base 5. Okay. And when you think about this procedure is exactly the opposite of what we did over here. All right. So what we did over here, we're just reversing that over here. And what are we doing? We're just multiplying it with base 5, putting our answer down. So when I multiply 0.5 with 5, I'm getting 2.5. I'm taking the integral part over here and then putting it in my answer box after the decimal place, because this is the 5th place. And what is left out? 0.5. Again, I'm going to multiply it with 5. I'm going to do that until I get a whole number. In this case, it keeps repeating. So I conclude that 1/2 in base 10 is actually 0.22222 and so on and so forth in base 5. All right. Okay. So this is an interesting problem. How am I to tell if a number is even or odd in base 2, base 3, base 4, 5, 6, 7, 8, 9, and base 10. Now, base 10, it's easy. We know, right? 2, 4, 6, 8, 10, 12, and so on and so forth. So in base 10, the thing is a number is even when you divide the number with 2, when it is divisible by 2 with leaving a remainder of 0, you call it even. All right. So it so happens when you start noting down, actually, in the binary number system, you have 10. Okay. And then you have 100. You have next 110. And then you have 1,000. You're just including only zeros and ones. That is the binary system. You have 1 0 1 0, and then so on and so forth, right? So in base 3 system, so every third number will be a double digit number, will be 10, right? So you have 2. You have, let's see, 11, and then 11, 12, 13, 14, 20. Okay, it goes so on so forth. Okay, so the point that we have to make is in base 10 system, any digit that is divisible by 2 and leaves a remainder of 0 is an even number. So we have just gone over the part where we said in base 5, when you add the digits, if the sum of the digits is an even number, is divisible by 2, it is an even number. So it works, most of it in all the other system, it so works that when the base is an even number, so works that when you add the digits, if it is an even number, then it is, when you add the digits and if it's an even number and it is divisible by 2, then that particular number is called an even number. So in base 4, how will we go? We'll go 2, 10, 12, 20, and so forth. And base 5, we should be thorough with base 5 by now. So 2, 4, 11, 13, and so forth. Base 6, you will have 2, 4, 10, 12, and so forth. Base 7, you will have 2, 4, 6, 11. So mind you, I'm just counting by twos. That means in this particular system, these numbers are considered even numbers. All right. So for example, in 7, 11 is considered an even number. How can you tell? When you add 1 plus 1, you'll get 2. So that is an even number. So in any other system, a number is an even. Here I'm counting by twos, right? A number is an even number, okay? If when you add the digits, you are getting a even number, all right? So all right, this is what we call the hexadecimal system. Hexa is 6, decimal is 10. So this is the base 16 system, all right? We'll count till number 9, and number 10 will be A, number 11 will be B, number 12 will be C, and so on and so forth. So what are we going to find? We are going to find 6D, which is in the base 16 or hexadecimal system, and we are going to translate it into base 10 system, all right? So what we are going to do is, now we know the value of D. Value of D is over here, 13, right? So how we are going to do this is 6 times, because it is a base 16 system or the hexadecimal system, you're going to multiply the first digit with 16 plus the value of D. Over here it is 13, which will be 109 in base 10 system. All right. How about AE16? Now A is how much? A is 10 in the hexadecimal system. So I'm going to multiply 10 with 16, multiply the first number with 16. And then what is the value of E? 14, right? So I'm just going to put it as 14 plus 14. Let me just quickly calculate 160 plus 14, which will be equal to 174 in base 10 system. Now the next one, 9C16. I'm going to use the same method again. 9 times 16 plus the value of C is 12. 9 times 60 is 9, 6, 54, 5 carry 915. So this will be equal to 156 in the base 10 system. All right. Next one, 2B 16, which is equal to 2 times 16. And what is the value of B in this system? 11, which is equal to 32 plus 11, right? Which is equal to 43 in the base 10 system. All right. Now this is fairly simple because you have it over here. So I'm just going to use that. And then I'm going to multiply the first digit with 16 because it is a base 16 system. Plus, I'm going to find the value of the letter and I'm going to add it up. Okay. So that is how you'll convert the hexadecimal system to the base 10 system. Now, next, I have a handy dandy table over here. This is exactly the same way you convert base 10 number to any system. All right. So what they want us to do is, using the same system, translate these base 10 numbers to base 16 system. All right. So what I'm going to do is, I'm going to take 97, and what am I trying to do? I'm going to convert it into a base 16 number. Correct. So 97 divided by, I'm going to divide it by 16. All right. Now the closest value is 16 times 6 is 96. So I'm going to say 16 times 6 is 96 and 1 is the remainder. Now 6 is too small. It will not be divided by, divisible by 16. So I'm going to leave it over here. and write it again from bottom to the top, just like the way we do for base 2 or base 3 or base 4 or 5 systems. All right. So now I have 97 in base 10 as what? 61 in base 16. All right. Now let's do the next problem. B, 144. All right. I'm going to take 144, use 16 again. Let's see. 16 nines is 144 and remainder is 0. This one is simple, right? So 144 in base 10 is equivalent to, again, 90 in base 16. All right. Now C, 203. Same procedure, same method. Why am I dividing it by 16? Because every 16th number will change in a hexadecimal system, just like the way in any other base system. That is the basic logic of any base system. All right. So 203 divided by 16. All right. So 16 times 11 is 176. 16 times 16 times 12 is 1 is 192. 16 times 13 is 1616 times 13 is 208. So what I'm going to do is I'm going to use 16 times 12 and then the remainder will be 203. Just quickly calculating. 203 minus 192, which will be 03 minus 11. All right. So what I have over here is 12 is too small to go in 16. So I'm going to leave it over here. I have 12 and 11. Okay. However, 12 in hexadecimal system is C and 11 is B. Okay. So I can write 203 as 12 and 11, or these are 2-digit numbers, right? Instead of 12, I can write C. And instead of 11, I just saw, right? I just showed you, right? You can write it as B. All right. So 203 in base 10 system can be translated as 2CB in hexadecimal system. What did I do? I did the same method, but then instead of 12, I wrote C, because that is what, according to the hexadecimal chart, instead of 12, I wrote C. Instead of 11, I wrote B. How about 890? Now, you can use the same procedure to go ahead and do it, or you can also use factorization, like prime factorization, to go ahead and do it. What do I mean by that? So I can write 890 as 3 multiplied by 256 plus 7 multiplied by 16 plus 10. Okay. Now this will translate to, now let's go back over here. A is 10, correct? So when you go ahead and calculate this, instead of 10, I'm going to write A. Okay. When you go ahead and do these calculations, you will get, when you go ahead and calculate these values using the same procedure that you'll get, that you have used, you will get 37 as the hexadecimal value. What did I do over here? I took this value, instead of 10, I wrote A because I split this number up. And instead of using this value, I went and I went ahead and did this procedure, kept dividing it by 16, and you will get 37. Okay, why? So I had divided this with 16, I divided this with 16. When you divide this with 16, you will get 3, and this 30, and then when you divide this with 16, you'll be left with 7. So your answer will be 37A. All right, so instead of going through, you can do the same thing too. You can put 890 and then divide it by 16 and then go ahead and get it and then translate it. But instead of doing that, I use factorization principle and I split 890 up, and then instead of 10, I put A. After that, I divided this by 16 and then I divided this by 16. When you divide it 7 times 16 by 16, you'll get 7. When you divide 256 times 3 by 16, you will get 30. And then you can write your answer as 37A, right? So bases are nothing but, if it is a base 5, you will count till 5, 0, 1, 2, 3, 4, and then go to the second double digits, which is 10. So if it is base 2, you will count 0, 1, and then it is 2. So that, in 0, 1, and instead of 2, you'll write it as 10. So bases are nothing but viewing, instead of going till 9 and then starting with 10, well, depending upon the base, we'll go to that number and then start with 10. All right, guys, all the problems are over here for you, and you can watch the video again if you need to. Bye. Have a good evening.